Yeah, let's see what happens. All right, any questions?
There's a couple that we can go over from some of your old tests.
Okay.
Yeah, actually, let's see. So the graphs on number 5. Bottom.
Okay.
Specifically part C, but like part B, I could go over again too, even though I think I mostly get it.
All right, so we have sorry about that. All right, so we have 8-meter radius.
2021 summer.
Pardon?
I'm talking.
Oh.
He was asking what test it was.
8-meter radius solid sphere. Oh. Okay. Surrounded by a hollow sphere in a radius of 15 meters. So I've got another sphere here, there, and so this is solid, and this is the shell. And that's 15 meters and 18 meters. The inner shell has 10 to the 10th excess electrons. And hollow outer sphere has 3 times 10 to the 10th excess protons. Assuming electric potential is 0 at 0 volts at R is equal to infinity. What is the net charge on the solid sphere? So just the graphs part.
Yeah.
Well, we'll do piece by piece.
Yeah, we gotta get the charges, but the charge in the middle is just the 10 to the 10th times the charge of an electron.
Yes.
Your answer was off by a magnitude, I think, but.
Oh, it's, okay.
So I think you ended up with 10 to the 9th, and I think it's supposed to be 10 to the 8th, but.
Let's
10 to
see.
the negative 8.
So the charge would be negative 1.6 times 10 to the negative 19th times 10 to the 10th. That's coulombs per electron, that's electrons. So negative 1.6 times 10 to the negative 9th.
My calculator kept giving me negative 8. I don't know why.
If you did,
You don't count the 10 as part of the 10 to the 10th? Like instead of 1, it's 10, so.
it's 1 times 10 to the 10th.
Well, no, it's 10 times 10 to the 10th. That's what you had to give 10, right?
Oh, no, 10 to the 10th is right.
Oh, right, okay.
So some people will do 10 and then hit the EE button, 10, which
Yeah.
is 1 too many, it should be 1 EE.
Oh, okay, that's what I was doing, yeah.
Okay.
All right, I get it now.
All right, so the charge here at this point is going to be negative 1. Negative 1.6 times 10 to the negative 9th coulombs. All right, what is the electric field inside?
0.
Yeah. So since the electric field is 0 inside here, then by Gauss's law, I know that the internal charge must be 0. So this would be positive 1.6 times 10 to the negative 9th coulombs on the inner part of the shell.
Why is that?
If I create a Gaussian surface in the middle of the thick shell, I know that the magnetic flux, wrong course, or wrong point, the electric flux is equal to through a closed surface, is equal to the enclosed charge divided by epsilon sub naught. We went through a derivation with dealing with forces, but if I've got spherical symmetry, then I don't need the electric field from anything outside is not going to contribute. So anything out, so my Gaussian, if I put my Gaussian surface there, where I know the electric field is 0, I can ignore anything outside of that Gaussian surface.
So basically the rest of the charge of the outer shell, you ignore.
Yeah, whatever's out there. So I know that the total charge inside has to be 0, since my electric field is 0 here, the electric flux is 0. And so my enclosed charge must be 0. And so if that's negative 1.6 times 10 to the negative 9th, this has to be positive in order to balance it out.
Okay.
And that's the number of protons I have. So the total charge on the shell, on the shell wall, is that times the positive version of that. So 1.6 times 10 to the negative 19th coulombs per proton times 3 times 10 to the 10th protons. And we end up
4.806.
Okay, I rounded off 4.8 times 10 to the negative 9th coulombs, of which 1.6 are here. So the outer shell's got to have the remaining, so 3.2 times 10 to the negative 9th coulombs. Dramatic pause for a follow-up question before we get to graphs.
No, that's fine.
Okay. Did I hand it back to you? Yeah, I did. Okay.
No. Yes. Yeah. Graph the electric field with respect to distance to the center from R to 0 to 30 meters.
So my electric field, let's see if I can draw my circles better.
It's just like KQ over R squared calculations at each like point.
Yes. So if I'm outside of it, I just have to look at my total charge. And my total charge of this whole thing is that, since those two cancel out. So if I'm outside of all of this, so if I'm out here, it's just a K times, so 9 times 10 to the 9th times 3.2 times 10 to the negative 9th
It's just an inverse square thing.
over R squared. So I get some number, and then I can plug in R and actually figure out what the actual value is at that point. But it would be a 1 over R squared relationship, if that's my electric field.
Yeah, and then it does some stuff before that, but I think I got the electric field mostly. It was the electric potential that I was having more difficulty with understanding.
All right, so I know that the electric field is 0 in here, and then once I get inside there, it's going to be negative. So boom, and then at this point, Q is now negative 1.6 times 10 to the negative 9th. So it'll be some negative value. And then by the time I get to the center, it'll be 0.
Anytime the electric field is 0, the potential is 0.
No.
It's constant.
Anytime the electric field gets constant. Oh. That is wrong there.
So it's like constant in the center, and then
It's constant. Then when I get to here, my electric field will be a 1 over R squared relationship based upon that charge, and then it drops back to 0 again. There we go. So if this is in between the shells, this is for,
you're looking at potential right now?
no, the electric field still.
Oh, okay.
Okay. I know that my potential, my electric field is basically the derivative of potential, so potential, or change of potential, is equal to E dot dr negative.
Oh, so we can just take the derivative of the electric field graph?
No, you would have to take the derivative, you'd have to do the integral of the electric field graph.
Okay. Can you just look at the electric field graph and like figure that out based on the way it looks?
Yeah, you can do that too. So I know that when I'm out here, it's going to be a 1 over R relationship. Let's see if it makes some sense here that basically this, my electric field should be the slope of my potential graph. So my slope here is negative, and so my electric field would be the negative of a negative, so my electric field is positive. When I'm here, my electric field is 0, which means my voltage is not changing. Let's see if we can actually line this up. So the region where the electric field is 0, my voltage is constant. Then in this region right here,
I think it's supposed to be going the other way on the electric field. The slope is like the other direction.
or
The little piece there.
that little piece right there.
Yeah.
As I get closer, the magnitude should be bigger, yes, thank you. This one for our script. Yeah. Thanks. So here, my electric field is negative. So my voltage would be, so the slope of voltage would be positive. So just clearly putting in a drawing like that. Let me think through that again. So right there, my slope is positive of my voltage, or my electric potential. Slope is positive, so my electric field would be negative. Zero, so. It gets less steep as I go. So I would expect. So my slope is that as it becomes less steep. So as that magnitude gets smaller, think through that. When the slope is larger, the electric field will have greater magnitude. And then in here, so wherever it ends up, the flat line.
Yeah.
Crudely, something like that.
That's right, yeah. It drops more, but you're right in this shape. So how did you figure that out though?
Sort of working backwards. Whenever I'm doing the integrals, I basically do a first guess, and then I think, all right, what's the slope telling me about this? Since this is the slope of that, I know that my slope here is greater than my slope is there. And my electric field is greater magnitude than it does there. This is a positive slope, so my electric field is negative.
Okay.
And so that's how I got that shape.
If you give us a question like this in the test, are you gonna be looking for exact values on the graph? Like-
If I say sketch, then no.
Okay.
If I ask for specific values, then
Just as long as it's like positive or negative in the right places.
it curves the right way.
Yeah.
But since all of you are young and your minds are sharp, you should be able to do it faster than I just did it. So if I can do a test in 4 hours, you should be able to do it in 2. That's the way it works.
I don't know about that.
Does anybody else have any questions? I have more.
Yeah, I got one on, I don't have it printed, but I have it showed it pulled up.
Okay.
So it's like a castings, there's 3 different cases.
Okay, and you pick one?
You pick this one,
The order or
and the straight,
Okay.
vertical one,
Yep.
horizontal order, and it says which one has the greatest electric field and the greatest potential.
Oh, yeah, that's
You
all
go to
the same
those?
test.
I didn't know how to.
That's all the same test.
Yeah.
And they're all like, from 0 to 10, or from 10 to 10, so they're all roughly.
Summer 2016.
Oh, I will point out, Ibrahim came to me with a couple of questions from the spring 21. Just to let you know that for the online tests, the way I did it is I allowed them to open book and so forth, but it made the problems harder.
Oh, yeah,
So
that
there were-
overlapping like sphere one or
Yeah,
whatever.
yeah, that is not something I would expect you to do.
That was an evil problem.
Which one? It was.
There was like two spheres, but like part of it was outside of the other sphere when you were calculating.
Oh, yeah.
Yeah, potential influx or whatever it was.
Yeah.
That is, if I threw that on something like this, then that would just be my evil sense of humor. Not expecting you to do that.
There's like a charge P. So, yeah.
P is there, what's that distance?
It goes from -5 to +5. double
That's
line.
-5 to +5,
Yeah.
and the distance from the line to P?
Doesn't say.
Oh, yeah, -5, wait.
Oh, P's at X equals 10, sorry.
Okay, so that's 10 right there.
Yes, yeah.
Okay. And then we had the semicircle, or the quarter circle. P was there, and this was 5 and -5.
10 and 10.
10 and 10, all right, so that's 10 and 10. And then the horizontal, the one running like this, going from,
-10 to 0, and then P's still at 10.
Then you have a sphere, which is a radius of 4. Were you only looking at the line ones?
What do you mean?
oh, no, you're looking at different, you're looking
Oh,
at
there's
variations.
different, yeah, it's different numbers, I think.
Oh, it's a different test?
Yeah.
Oh, okay.
Yeah.
All right, and the first question was, where is the potential
First question
greatest?
is, where's the where's the greatest electric strength at P, and B is where's the greatest electric potential at P?
The electric field and electric,
Potential.
all right. So potential's gonna be the easier one. Because electric potential depends upon, assuming they exist in the same part of space, let's just make the assumption that the potential equals 0 at 0 volts at R is equal to some infinite distance away, which I don't know if I stated or not. So it depends on how close we are to the charges, because each little aspect of this is going to produce its own bit of charge, so that's gonna produce a potential there, that's gonna produce, there'll be some potential there from that, and potential there from that. So I don't care about direction, there's no canceling out here. So in which case are the charges the closest to that point?
They're all as closest to P.
As in, all of the charges here, where are they closest? Because if you think about,
The top.
It's gonna be the top.
that's 10 meters away, so all this is farther than 10 meters away. That's 10 meters away, so all of those are farther than 10 meters away. Here, everything is 10 meters away. So this would have the greatest electric potential.
Yeah.
Because every single infinitesimally small charge is 10 meters away from that point, whereas in the others, only one infinitesimally small charge is 10 meters away.
And then the top one's the next.
Yes, top one would be the next, and the bottom one would be the last one, if you rank them. The electric field, not quite as obvious. So, in terms of electric field, all of this is on the same side, so that's gonna create an electric field going to that direction, and then that, and then that. I mean, each one of these bits is gonna create an electric field all in the same direction. This one's gonna create an electric field going in, well, basically all of these directions. And so we're gonna have some canceling out, and the net result's gonna be an electric field in that direction. And in here, we're gonna have some canceling out. All of the vertical components are gonna cancel out. So to find the electric field here, that is probably gonna require doing some calculus. I'm trying to think if gut feeling is gonna tell me anything here. Because these are all closer, but there's some canceling, there's no canceling, but we've got the farthest away here, so 1 over r squared. Here, the vertical component's canceled. Yeah, not calculus. A day without calculus is like a day without sunshine. All right, so the first one, I picked some infinitesimally small part. I'm gonna sort of create an axis right here. And I know the vertical components are gonna cancel out, so what I'm gonna do is just integrate over the horizontal. Or we'll make it the I direction. I hat, J hat, K hat coming at us. I have some infinitesimally small part of charge here, DQ. I will artificially create an angle theta, which will need to disappear at some point. This length, this here is R. So I know my electric field, at least the horizontal component, is going to be the differential K dq over R. Cosine of theta I hat plus something J hat, which we don't care about. Dramatic pause for questions?
The cosine is because the component, like you're breaking it into.
Yes, absolutely.
Are we technically working in polar then, or polar coordinates, like just out of curiosity?
I don't-
Theta and R.
I don't think polar would really help a whole lot here.
Well, you're just using theta and R, so I was like,
Yeah, because both theta and R would change over the course of, as we integrate, then it would not, we're still dealing with two variables. I don't think that would be easier, but if you can do it that way, that's fine. Here, you're more apt to get away with polar than here, since R is constant for all these points.
yeah, I was just asking about the first one, because you were using theta and R already, like you would be in polar. but-
Yeah, using theta R just as temporary.
Yeah,
I've done it this way so long that my mind's not stretching out the other ways at the moment.
Okay. Just double check.